Well, hello there, and welcome back to Thermodynamics. Today's video topic is the conservation of mass. The conservation of mass is a fundamental principle that cuts across a lot of engineering. If you've had me for physics, we covered it there as a fundamental principle. If you've had me for fluid mechanics, we also cover it there. All right, so it has some other names. It is also known as the continuity principle, there are some nuances there, and also known as a mass balance. So here is the equation for the conservation of mass. If you have any system, the initial mass in the system plus any mass that comes in minus any mass that goes out will be the final mass in the system. I like to think about a bathtub. So you've got a bathtub. I've got my granddaughter coming over to play with me today, and she's going to spend the night, and we'll give her a bath, and we'll start maybe with the bathtub empty. And over the course of the time that the water is flowing in, mass will flow in, and my granddaughter often pops open the drain at some point in time, so mass flows out, and at the end of some period of time, we would have some final mass. So that's the equation for the conservation of mass. Now, it isn't just that simple, because we often account for mass that is flowing. And when mass is flowing, we connotate that with a dot over it, and we call that mass flow rate. When mass is flowing, we typically have it flowing like in a duct or in a pipe. Maybe we think about, how about we have some fluid flowing in a pipe here, and how much mass, that's the cross section there, that's a circle by the way, how much mass is going to flow past a certain point in a certain amount of time. So let me grab another color. If we were to say, well, this is a chunk of mass, and it's going to flow past our point in a certain amount of time. Let's give this chunk some dimensions, maybe some thickness D. It's got a cross-sectional area A, and so mass is going to be density times volume. Mass flow rate will be density times volume divided by time. Well, the volume of our chunk here will be its area times its thickness. And we multiply that times density, and we divide by time. When you have a fluid flowing in a pipe, that distance divided by time, well, that's another way of saying velocity. So mass flow rate is density times area times velocity. So in any pipe, if I know the cross-sectional area, I know the density of the fluid, and I know how fast the fluid is moving, I can have its mass flow rate. Mass flow rate has units of kilograms per second, or in thermo here we'll often do it as pounds mass per second. Well, this allows me to come back up to my equation for like the bathtub, and say, well, how about if we say the mass initial plus the sum of all mass flow rates in minus the sum of all mass flow rates out equals the mass final. So we got some mass in, got some initial mass, got some mass. Oh boy, I think we have a unit problem here. For mass we might have kilograms, but for mass flow rate in we have kilograms per second. We can't do that. We can't add kilograms to kilograms per second. That'd be like adding apples to crab apples. But if we take each mass flow rate in term and multiply it times how long it flowed in, we would now have kilograms per second times seconds. There we go. So this is a very good general case equation for the continuity principle, also known as the conservation of mass. Where are we going to use this in thermodynamics? Well, when we have energy that is in a system, let's think about a turbine. Some steam maybe flows into the turbine at 0.1 and flows out of the turbine at 0.2. And if it comes in at a very high energy at 0.1 and goes out at a low energy at 0.2, we can get some work out of that steam as it flows through the turbine. The work, in fact, will be the change in energy from 0.1 to 0.2, and we use enthalpy, or H, as you've seen in other videos and we'll see in future videos, to show how much energy the steam had when it came in at 0.1 and when it came out at 0.2. However, that energy is flowing in a mass. So it's the mass of steam that is bringing the energy in and bringing the energy out. So where this becomes particularly useful is if we multiply the mass flow rate times the change in energy, we can find out what the mechanical power is being supplied to the turbine by the steam. There we go. That's where this becomes useful. Mass flow rate helps us with rates of energy, rate of heat transfer, mechanical power. Let's check our units there real quick. Mass flow rate would have units of kilograms per second. Enthalpy has units of kilojoules per kilogram. Nice. That gives us kilojoules per second or kilowatts. That's a unit of power. English system, pounds mass per second. BTUs per pound mass. BTUs per second. That's a good unit of power. We can convert that to horsepower. So there is our video on conservation of mass. Another analogy I like to use here is my bank account. At the beginning of the month, I have an initial balance. During the month, my checks are automatically deposited and my bills are automatically paid. And at the end of the month, I have a final balance. So a mass balance is a lot like balancing my checkbook. All right, well, let's wrap this up. You can expect a quiz when you get to class. Here are some things I might ask you to do. Calculate mass flow rate in a pipe, or find time to empty a tank, or define mass flow rate, or describe the conservation of mass. Along with that describe, we do some everyday life examples. How about if you think of an example of the conservation of mass that has to do with a car.